Good evening, everybody. Thank you for joining us for Parametrics for Beginners. We'll be having this presented by David Kapolka, one of our CTAC members from the Grand Rapids, Michigan area. I'm looking forward to it. So before we dive in, I guess I do want to just remind you, as always, for the sake of audio quality, you will be muted. And if you have any questions, you can type them in the question pane, and I'll be happy to address those. So to dive right in, I'll pass control over to David, and he can tell us a little more about what we'll be doing this evening.
Hello, everybody. So let me know if you can see my screen.
Let's see. I do see your screen. Yep.
Okay. So I'm going to be talking about parametrics and parametrics for beginners, applications from algebra to calculus, and the focus will be mostly on the beginners part of it. We'll do some interesting mathematics. We'll look at some fun things. So I'm going to scroll through this handout, which will be available at the webinar site. So if I scroll down a little bit, I'll be talking about the definition of parametrics and how parametrics are related to graphing things like lines, parabolas, which we'll take a quick look at. You can see as I scroll through some of what we're going to talk about. Jump right into plotting conics, parabolas, ellipses, hyperbolas, various things like what are called Lissajous figures, and show you how those work. An interesting plot of what appears to be a chrysanthemum, sine wave tracer, a classic train problem which will model some motion, a projectile problem, which a baseball flying through the air. We'll talk about roots of complex numbers, powers of complex numbers, and lastly another projectile example. So that's the handout, and I'm going to set that aside and show you my calculator. Now, for those of you that own Macintosh computers, I happen to be running a Macintosh, and I'm going to be using VM Fusion, some nice software that allows me to run Windows on my calculator, and I can run both the Mac platform and the Windows platform at the same time. So I'm going to max out my screen so you can see things a little better. When we want to run things in parametrics or function mode, this is the basic layout of the calculator. I have to go to Graph, and you'll see that I have some functions already included. So I'm going to delete a few of these. Apologize for not doing the house cleaning a little early. And hopefully none of the functions are turned on, so we'll see if we can get started. Right now I'm in function mode, and to change this to parametrics, you just change the type of the graph that you want to examine. If you look at my screen, you'll see that I've got a function here. I've plotted something in terms of x, and I've got some inequalities. So when I click type, which is F3, I can select parametric, and immediately the available graph slots change to parametric form. Let me go back a moment. One of the things I wanted to show you, and it eluded me, was I wanted to be and show you the handout. Well, if you happen to look at the handout, if you think of a right triangle and the sides, with the horizontal being x and the vertical being y, if we take the cosine of an acute angle b, beta, it equals the adjacent leg, which is x over r. And if you solve that for x, r is cosine b, and you do the same thing with the sine will be r equals sine b. And that's how we relate things parametrically to what we're going to be doing with kind of graphs and so on. The initial foray into dealing with parametrics is to take a look at the basic things like how do you plot things like y equals x. Once you're in parametric form, the key on the calculator, the xt theta key, changes from being x to being t. So if I create both x equals t and y equals t, then x equals y, which means that's what I'm plotting is y equals x. And one of the things I want to make sure that I do is set the window. Now you don't see the window setting here, but it's the shift function of F4. So I'm going to set the viewing window, and I'm going to use an initial window, which will give me a nice aspect ratio. But I'm going to scroll down here because one of the things in parametrics is you have to have a min and a max for the t values. If I plot 0 to 2 pi, I'll be getting a small segment. So I need to change this to something more meaningful, like -10 to 10. And those are basic t values. And the point change is going to be the increment that I'm going to move along here, and its default is, in this case, 0.026, and that's okay. When I press the exit key, that is a way to go backwards to where I want to go and see my values here in xt and yt, and I can draw that. So I press F6 for the draw, and there you can see I've drawn the line y equals x. So Nathan, let me know if there's any questions at any time.
I'll do that.
All right, thank you. So I want to continue by taking a look and to return back to the graphing equations. You press exit, and it just returns us back. What's nice about plotting parametrically is when you're looking at things like a parabola, you can plot a parabola along with its inverse and then study the things that we teach students in Algebra 1 and Algebra 2 about plotting functions and their inverses. So for example, in vertex form, if I want to plot a function such as y equals 2 times the quantity x minus 1 squared plus 2, so I've got vertex form, I plug in t for the x, and then y will equal whatever value on t I choose. In this case, it's going to be 2 times the quantity t minus 1. So my x-coordinate of the vertex is 1, and the y-coordinate will be -2. So I add 2 because it would be y minus 2 equals 2 times t minus 1. So my vertex is going to be at 1, -2. And I hit execute. That's now selected, and we'll see if that shows up on my screen at the same window. Now, I didn't square that, so that's why I got another line. Let me back up. It's nice to know that what you should expect to see is a parabola, and you don't see a parabola, you know I made a mistake. So I plug in the t squared, and now let's try that again. And there's a parabola, and it's up here, and so one of the things we can do is adjust the window, but the Casio Prism has a nice feature. If I want to see that window, all I have to do is press the arrow key, and I can easily adjust the window by letting it scroll. So that's a very convenient feature. Now what I want to do is I'll ask students, so how do I go about, one of the things that we teach you about plotting the inverse of this parabola? Well, we know that we switch the x and the y's and we solve for y. So I put that in this next available function down here in y3. I'm going to delete that function there. And when the available function, which now will be in green, is in parametrics. So I just switch the x and the y. So in the y position, I type in the 2 times the quantity t minus 1 squared plus 2. And in the x position, or in the y position, that switches. So you'll notice that I've switched the x and the y, which is what we tell students to do when we're talking about inverses, and draw that. And there is the inverse. I think that's extremely handy for students to see. Now if we trace on these, this shift function of f1, it's off the screen because it's down at the lower left, and I've got the derivatives turned on, so I may want to turn those off. And I'm scrolling up. Eventually you'll see a little something appear on the screen. There it is, right there. So if I press the up arrow, I'm going to digress a minute. I'm going to turn the derivatives off. That's in the setup. They're kind of in the way. And let me turn those off, execute that, and redraw. And let's trace again. And it's going to take a moment to get up there. Here we come. And the reason I want the derivatives off is now I can see the x-coordinate and the y-coordinate. And one of the things, you can see that they're the same, so I'm on the line y equals x. So I'm scrolling along and take a look at the x-coordinates, about 2.9, and the y is 1.68. And if I press the up arrow, they have been switched. So when we talk, this demonstrates one of the features about the inverses is that when you plot a function and its inverse is reflected over the line y equals x, which we see that. How you go about getting the equations, you switch the x and y and solve for y. As well as the x and y coordinates switch as well. So we've seen a demonstration of that without looking at the table, which we can also take a look at. So how are we doing, Nathan? Any questions?
Just one question. What I think I must have missed briefly when you were setting the window. What are your t values?
I set the t values at -10 to 10.
Okay.
Which will allow me to have this line y equals x and these plotted more fully in the domain.
Right, right.
You just have to have some sufficient negative and positive values for this. We'll talk about, when we talk about, it says t theta min and t theta, which can be misleading because we're not plotting an angle here. Generally, when we plot things in parametrics, we're involving something with sine and cosine, and so you need 0 to 2 pi or something like that.
Mm-hmm.
But in this case, that can be a little misleading for the casual observer.
Right. I do like what you did with the inverses. That's a nice way to jump back and forth and see what happens to the x and y coordinates.
Right. And while you're there, in order to see, let me jump out of here. If I want to take a look at the table of values, I go here and I can set the table to start at whatever value I want. Let's say I started at -5, and it's going to increase by 1, which could be a little misleading. So right now I'm on the line y equals x, and if I scroll over, I can take a look at, you can see here I've got -574, and that's on one of the functions, and its reflection is at 74 -5. So in the table you can see, and it's a little hard to see in this pale green, so we may want to change the color of the graphic. So you can see that they're switched there in the table. Let me go back to the graph. So in the handout, I have a discussion that goes on about plotting ellipses and hyperbolas. And if you're not familiar with how they're generated parametrically, the Prism has a conic grapher, which is really very nice. But if you're studying conics and you're studying them parametrically, this is also kind of an interesting way to learn about parametrics. The way that in the standard form, think about an ellipse, and if you look at the handout, you'll see it's x minus h quantity squared over a squared plus y minus k quantity squared over b squared equals 1. So that's the sum of two squares, and one of the Pythagorean identities we know about is cosine squared theta plus sine squared theta equals 1. And if you equate these two equations, then the x minus h squared over a squared corresponds to the cosine squared theta, and the y minus k squared over b squared corresponds to the sine squared theta. And if you equate those, then the x becomes a cosine t plus h, and the y part is b sine t plus k. And what I'd like to do is plot those. So I'm going to turn these off. I could just delete them, so get rid of those and use the same. Oops. Let's delete those. Keep things a little cleaner here and delete those. So to plot a typical ellipse, such as 3 cosine t, and what I'm plotting here is x minus, I'm going to be plotting cosine t, sine t, and the eccentricity is going to be 3. So 3 cosine t, and I'm going to show you how you can easily translate the center of the ellipse, the intersection of the major and minor axes, without a lot of difficult understanding on the part of students, where you don't have to think about, am I translating the axis, am I translating the graph, what am I doing? When you look at this, it's obvious that the center of the ellipse is going to be at 1, negative 2. It's obvious to the teacher. It's not so obvious to the student. Now, I haven't really done anything with the window. I'm going to leave the window alone and just go ahead and draw this. You can see the ellipse shows up down here. So once again, if I want to scroll down, all I have to do is go like so. And there's my ellipse, and the center is at 1, negative 2, right in this location here. And it's that easy to plot an ellipse. And so you can change the eccentricity, which would be the coefficient of the cosine and the coefficient of the sine, and you can change where it's located. Now let's put a hyperbola on the same grid with this. Now to work with a hyperbola, you need the difference of two squares, because you've basically got x squared over a squared minus y squared over b squared equals 1. Well, the Pythagorean identity associated with that is 1 plus tangent squared to secant squared, or secant squared minus tangent squared equals 1. But you won't find a secant squared key on most calculators, including this one, but you will see that secant is 1 over cosine. So in order to plot the hyperbola, you need something like this. So let's make the eccentricity similar. So I'm going to have 3 divided by cosine t. Oh, one of the nice features about this calculator that I want to demonstrate is if I type it like this, it will work just fine, but a better appearance would be to have this as a fraction. So let me delete this, and I'm going to use the fraction key, which gives me a nice numerator of 3, and then I can just arrow to the right, which will arrow down, and put the cosine t in the denominator. When I do that, it makes it obvious that plus 1 is a horizontal shift of my center of my hyperbola. And let's make the y part 2 tangent t, And let's put that, let's see, I translated that over 1, so I want to put that at -2. Press execute. You have to press execute so they're selected. You can see they're selected because the equal sign is highlighted. Let's go ahead and draw that. And voila. Now I've got an ellipse and an associated hyperbola. And it's that easy to plot various things. How are we doing, Nathan?
No problem so far.
Okay. Let's continue on. And so those are how you plot. I showed you how to plot parabolas, ellipses, hyperbolas. Nice thing about deleting one piece of the function is both pieces get deleted. Excuse me. Let's see, F1. Now, if you have a polar graph, such as cosine 2 theta, it can be plotted parametrically because it's simply R. We can put things in polar form right here, but I'm going to stick to parametrics and show you how you can plot polar in terms of parametrics. And it becomes quite nice to be able to do that for comparison's sake. So my function is cosine 2t. And I'm going to plot this four-petal rose curve. So cosine 2t, remember that's R, and it's R cosine theta, so I need another cosine t, not 2t. And the y part is the same R, which is cosine 2t, sine t. Now the problem that I have with this is it's going to be fairly small, so let's take a look at what the drawing actually looks like. And it is, it's kind of tiny. So you have some options here. Scroll, let's center this. We can either manually change the window, which we can do, or we can zoom. And you just zoom, and I can zoom in, or I can zoom out. I don't want to zoom in, I want to zoom in? There we go. So now I've got this rose curve, and I can do a trace on that, and you can see where things start. If I started it at t equals 0, for some reason it didn't start there. It's starting at t equals -10. So let me change this window so that we do in fact have a theta min at 0 and a theta max at 2 pi. That should be all it takes. And pi is at the bottom, and it's a shift. So there's 2 pi. Exit and draw. And voila, there we go. So now when I trace on this, this will make some sense. So I'm starting at t equals 0, and I'm at the far right. And this is nice to show students gently and easily how the function gets plotted and do a comparison between this and maybe the curve cosine 2t in rectangular form. Now this brings up another nice question. Let's suppose I change the type on the next function, and let's make that R. And right there I'm going to put in cosine 2t. In this case, it's theta because I happen to be in that mode. So you'll see on my screen, one of the advantages of this particular calculator is you can plot something in function mode, parametric mode, and polar mode all at the same time. Now, that's exactly the same, and you see a trace over top of it. So let me come down here and make a comparison. I'm going to change the type to y equals. I think I have to do a modify on that, don't I, Nathan? To change it once I've got a function, unless I delete it. Let me see if I can do that.
Yeah, yeah, you do have to.
So if I just delete that and it's empty, now I've got it into function mode, which is what I wanted to have. So let's see if I can put in the cosine to, and now it's going to be x because it's in function mode, and go ahead and draw that. So what I've got now is the cosine of 2x, which is the rectangular form of this function right here. And I can have them on the same screen, which is really a nice feature for comparison's sake. What do you think about that, Nathan?
It's nice. I wanted to make sure that you knew that it's not, I wouldn't call it modify, which you were talking about earlier. You go into type convert. Just
oh,
to be
convert,
clear.
okay. So
you click F3 really fast.
Okay, go in here to convert. That's
yeah.
right. That's what I wanted. Not modify, convert. Thank you for clearing that up. So if I press that, now I can change this to another form in that case. All right, so let's move on to a fun look at some relations that students don't often get a chance to see. And these are called Lissajous figures, and I found these many years ago. And this is where you change the coefficients of t. And this is going to give you an example. If I typed here the cosine of 5t, oh, and I'm in function mode, so I need to change that. So let me exit out of that. I want the type to go back to parametric. There we go. So cosine 5t.
And just to be clear to those who are watching, if it's an empty equation, you can just change the type. If an equation already exists in that slot, then you must convert it. That's just to be very clear.
Right. And we'll take a look at this. We'll just draw this, and you can see rapid fire what we've got. This is called a Lissajous figure, and I think it's a French mathematician who came up with these, just experimenting with different coefficients. And what's kind of fun about this is you can just change these to other coefficients, like throw a 7 in there and keep the 3 and see what you get. It looks similar, so you may want to have a second one and translate it over so it's side by side. I'll give you one more and then we'll move on from there. Let me delete that. I'm going to try 6 and 4. I think I have. That might give me something a little interesting. You can have combinations of these, and I ask students, so is there a difference between when one coefficient's even, the other one's even, or one's odd and the other one's even, or both odd? So you can see you'll get different shapes. These are called Lissajous figures. On that same vein, one of my favorite relations to graph is something called what I call the chrysanthemum. It's a polar function, and it's a sine of 7/10 t. So I ask students, how would you go about doing that? It's a little quiz for them. Well, if I delete this function, and I'm going to plot this parametrically, so sine of 7/10 t, and that has to be multiplied by cosine t to force it to be in the appropriate location on the graph. So this is r cosine theta, and I need r sine theta, and my r is sine 7/10 t. And I ask students to see if they can come up with the period of this function, which is not necessarily easy. And right now, my window, you'll recall, is t is going from 0 to 2 pi. So let's see how much of this graph we actually get in 0 to 2 pi. Not a lot, and it's going to spiral around. So if that's 2 pi, how many times do you think this has to spiral around until it completes itself? So we'll have students guessing. 10 pi, 15 pi, and so they'll experiment with that. It turns out that it's 20 pi to complete this figure, and it goes fairly rapidly. And we'll leave that pitch just like that. We'll exit back and draw that. So you can see this makes an interesting little pattern. If you slow it down quite a bit, that's why you can see why I call it a chrysanthemum. It's the appearance that it gets. So, a little foray into some fun activities for students. Next thing I want to show you is go back to doing some mathematics. Plotting a sine wave and a circle. You can do this with, typically teachers use a unit circle, which you can do. I happen to have a 2 circle. That's a radius of 2. So I ask students, how do you plot a circle? Well, it's simply r cosine t, will be the radius, and r sine t. In this case, I'm going to use 2. And we'll plot that, and it will draw for me. Now, let me change this because remember our window is going to 20 pi. So we don't need to go quite so far. Let's just make that 2 pi. And go ahead and exit and draw that and see if we get our circle. There's our circle. Let's change the window a little bit. I'm going to ask it for a trig window. Now this is probably going to change my, yep, it's good. I was thinking it might change my max there. So let's take a look at that. Now it looks like an ellipse, and so what I can do is I can square up this window on the y base. And since it's 2, actually I'm going to change this to be a 2 and 2, and then re-square this and see if I can get that to work. All right, so let's see. Oh, that's nonsense. That should be negative 2. Excuse my mumbling to myself. Let me go back to, no, delete 2. Okay. Now let's see if we can square that up on the y. There, I'm happy with that. Exit, exit, draw that. So there, I've got a circle, and I'm going to want to see a little bit more to the right, because the next thing I'm going to do is plug in the sine graph associated with this, which is 2 sine theta. So I need t for the x position, and the y will be whatever is happening to t, and it's 2 sine t. And I'm getting tired, so it's hard to see. Let's draw that. So what I've got is I've got a circle and its corresponding sinusoidal curve. Let me zoom out a little bit. I want this. No, don't do that. All right, I messed that up, so I'm going to have to redo this. I didn't hit what I wanted. Let me square that up again. And negative 2. All right, square that up on the y base. What I wanted to do here was to zoom. So let me look at the graph, and I want to zoom out. There. Now when I trace on this, I can take a look at the circle and then jump to the sinusoidal, and you can see the corresponding positions of where they would be. So here I'm at this first branch of this circle, and if I jump up, you can see where I'm at here in the neighborhood of about 90 degrees. So since the sine of 90 degrees would put me over here, then on the circle I would be here at 0, 2. So there's a lot of usefulness between plotting here the circle as well as a relation and the function to get that comparison. And if you make this a unit circle, then the values would make more sense. But I chose 2 just to be a little different. So another nice useful application here. All right, if you look at the handout, one of the problems that I used to teach in Algebra 1 was this problem out of an old textbook about the train leaving Chicago and heading to New York at 50 miles per hour, and an hour later the second train leaves Chicago and it's heading on a parallel track to New York, and when does the second train overtake the first train? And students would spend a lot of time dealing with this particular problem. So the motivation, if I was going to keep this problem in the math class, and I do because of what I do in the second part of this discussion about this particular train problem, will be evident. So to do this parametrically, students have to remember that rate times time will give me distance. So here's 50 miles per hour, and the time will be t. So t is a very useful parameter in talking about different functions. It can be used as an angle, it can be used to represent time, it can be used to represent a lot of things. And the second value that I put in this happens to be just y equals 1. And this will put us on track number 1 heading from Chicago to New York. Gets students interested in this kind of a problem. Then I asked them, so how do you represent a train leaving an hour later? Well, it doesn't have as much time on the track as the first one, which already has gone for an hour, and so they don't collide, we'll put them on track 2. And I don't usually tell students what the window will be. I want them, because there's a lot of mathematics to be learned in the window, but being the casual observer that we have today, I'm going to give you the window settings. So we'll start at Chicago, which would be 0 miles from Chicago, and it turns out that you've got to travel about 850 miles, so we'll make the X max 850 and ask students for an appropriate scale. So we may ask them how far is it from Chicago to New York and get some decent estimates. And we'll put let's scroll down to the y-min. I'm going to leave the y-min at -2 to 4. And that'll just, oops, I didn't complete that. Let me back up to finish the window. I need to get the, see the scale there is fine for the y. So the T-max here is a matter of how long does it take. And turns out that 17 hours will be sufficient. And the pitch for that, we'll make that a 100th. So it's not too fast or too slow. This will be how frequently we evaluate a point. And let's see if we get a nice picture. So what's the problem with the graph? And if students didn't make a change, these two graphs are plotted in sequence and not in simultaneous mode. So we need to change the setup. So right now I've got the graph simultaneous turned off. So you understand there's some learning that students pick up about that's not what I expected to see. So you shouldn't always trust the calculator. What I see there is not necessarily true. So now let's try the drawing again, and you can see, boom. So somewhere in here they were the same. And we can redraw that. So I have a question on this calculator, Nathan. Maybe you can help me out. Is there a way, well, I didn't redraw it, to stop the action for just a second when they approach each other? Is there a key I can press to stop that at an appropriate time? Do you know
not that I know of. That's an
Okay.
intriguing. I've never seen this use. I'm really enjoying it, but yeah, I don't know that there is a feature like that.
Okay, so what I do now is take a look at the table, and let's see what the setup is here. This is the t-value, so I can start the t-value at 0, and I want to increase that up to the 17 hours that it takes, and let's do that every half hour or so, and exit that, and then take a look at the table of values. So what I'm trying to see is where, and by the way, the reason of the negative 55 is that it would be off the screen. That other train hasn't started yet. So I'm looking for a place where they're pretty close to the same. And you can see this column represents where the first train would be, and this column represents where the second train is, and it's catching up a little bit. We're getting close. We have an answer. It turns out that the first train takes 11 hours to catch up to the second train, and they are 550 miles from Chicago. So that mirrors pretty closely what we saw on the graph. So let me go back to the menu, go back to number 5, and take a look at the drawing. So at about the 11th hour mark, somewhere in here, I think there was 2, 4, 6, 8, 10, right in here, I can see that they were pretty close to each other, and that's when they would be at the same distance. So the next question would be to ask students, suppose I want to put this train coming from New York. Well, in calculus, we have this thing called directed velocity, so I could make this negative 55 and put it out here at 850 miles away, start it in New York. And that's a question I would get the students, and you can see, boom, now they're heading toward each other. Of course, they like to put them on the same track and see if there's an explosion or what happens to the colors. But that's a problem exercise for the students to think about and come up with that. So that's my take on a classic train problem heading to Chicago, or from Chicago to New York. I'm going to skip over the baseball problem because time is fleeting and jump to roots of complex numbers. And this happens to be with de Moivre's theorem and how you go about plotting roots of complex numbers. And we'll do that next. So let's suppose I want to find the 3 cube roots of 8. And I'm going to do this, I think, still do this in radians. So we first take a cube root of 8. So if you think about the cube root of 8, the first root would be 2. In fact, all the roots are going to be 2, and then they are rotations of that to be in cosine I-sine form. So we take the cube root of 8, which is 2, and then, so the first root would be at, say, 2, 0, because 2 plus 0i will give me 8. Then I take the 360 degrees, or the 2 pi, and I divide it by 3. And then I have to step on that every unit. So my theta step will be 1, so I can step on those. Or if I did this in, say, degrees, it would step on there every 120 degrees. So in order to plot this parametrically, we start with the 2 parentheses, so I could probably get away without the parentheses. It's cosine 2 pi divided by 3, and I'm going to use the fraction key again. So I've got 2 pi, and I'm dividing by 3 because the rotation to hit the next root would be 1/3 of the 360, or 1/3 of the 2 pi. And you'll notice you get these nice big braces, and they're all in the same color, so things match up. If I have additional parentheses, by the way, you will see different colors for those, so that you can keep track of your left and your right parentheses, which is kind of a nice feature. And I repeat this, whoops, back up. Yeah, I'll go ahead with the parentheses. And I'm going to put in a fraction. In this case, I want sine of 2 pi over 3. Actually, that's not what I want. I want sine first, and then the 2 pi over 3, like so. Yeah, let's get the pi and arrow over, get the 3. And students know that if I put the t here, this is going to cause some problems, and if you plot it, they should notice right away. So if they don't arrow over, you'll get an error, and you learn from those mistakes. Now, before I plot this, I have to deal with the window. Oops, let me delete that. Press execute so they're selected. Now I can deal with the window. And I've got to change the window, and I'm going to change the window. I'm going to give you the window in this. It's negative 2.5 to 2.5 for the x. And the scale, we'll just make that 1. And we'll use the same for the y for this. And then we'll square it up. I do that a lot by continuing that. So I'm at negative 2.5 and 2.5. And now theta is going to go from 0 to 2 pi. No, I take that back. I don't want 0 to 2 pi. I want 0 to 3. Let me delete that. I want 0 to 3, and I want to step on this every 1 unit, so that this will be, t will be stepping on this 3 times to complete it. Actually, you can go from 0 to 2 and complete part of this, but this will give me a full, so I'm going to square this up on the y, and that should do it. Let's see what we got, if it squared it up. Yes, it did. So let me execute out of that, and this is always fun for students to see this drawn. So we get an equilateral triangle, and when we trace on this, here we've got 2 plus 0i. If I arrow over, I've got negative 1 plus, this is probably going to be, what is that, pi over 3i, or 1.7, that's in radians. And this will be the conjugate of that. So when we step on that, you're going to see negative 1 minus this value. And the reason that it goes 0 to 3 is it completes this triangle, so it looks kind of pretty. So I'm back at the original. There are only 3 roots, and you can see that they are the 3 vertices of this equilateral triangle. So an exercise for the user is to come up with the 4 fourth roots of 16, and as an assignment I have students come up with the six sixth roots of 64 and the cube roots of 1 plus I. So those would be the assignment problems, and then plot it and show me what they got on their calculator. So we're getting close to the end. I think we'll go into powers of complex numbers is very similar to this, so let's do that fairly quickly. To do powers of complex numbers, you're taking the square root of your value. So here's a complex number such as negative 1 plus I, and I can raise that to a power parametrically starting with r theta form. It would be negative 1 plus I, which is the square root of 2 and 135 degrees. So that would be where that would get plotted. And I can change this into instead of radians, I can change this into degrees. So let me delete this. And let's try that one. So I want square root of 2. So shift. And I want square root of 2. And I want to raise that to the t power. Let's see if this will work the way I want it to. Because this is a power, so there's t. Now this you have to be careful about because you want to get out of that exponent, and that's going to be multiplied by cosine t, and it's going to be cosine of 135. So I'm going to do this part in, I have to change the mode. Okay. And I do the same for the y portion, square root of 2. So square root of 2. Let's raise that to the t power here over, and sine of 135t. Okay, so those are selected. Now let's take a look at what the window should look like for this. This window might be okay. Well, I'm going to make that a little bigger. Let's make this go from -10. Oh, I can cheat a little bit. Let's go with the standard window, which gives me -10 to 10. And then what I'll do is I'll square that up on the y. There. That'll be plenty big. And I'm going to go from 0 to, let's go 0 to 6. And I'm going to step on that units. So we'll be raising, well, we should get 6 of these exponents. It'll quickly scroll off the screen. Now the other thing I need to do is change my setup. Okay, let me execute that and change this into degrees. So I am in, where am I here? If I scroll down, angle. I want to change this to degrees. See how easy it is to change those modes. We'll execute that, and let's take a look. Oh, it graphed it so quickly. But those are the 6 powers that I had, so I can tell what they are by tracing on it. So I've got the first one is -1 plus 0, and so -1 plus I, there is 0 minus 2i, so that's -1 plus I to the 0 power, -1 plus I to the first power, -1 plus I to the second power, third power, fourth power, fifth power, sixth power. And you can see what you get in each of those. So now you've got a way of demonstrating to students the power of the calculator and coming up with roots and powers of complex numbers. Nathan, we have time for one more example before we...
Yeah, I think we could do that.
See if there are any questions. How are we doing? Okay.
We're
the
doing
last
good.
example I'm going to show you is, okay, on projectiles, we do this in physics, is we have an object that's being shot out of, you can shoot an arrow, you can shoot a projectile, a bullet, or something like that. And when you have an object that's falling, and in a vacuum, if there's no air resistance, as the object moves horizontally, if we simultaneously drop an object, they will intersect each other at the same time every time if there's nothing in the way and there's no resistance. So let me talk to you a little bit about that. So horizontally, I'm going to have a projectile shoot out at 700, let's say it's 700 feet per second. So that would be the velocity and times time. So this will give me the x position horizontally of that projectile. Now it's going to be pulled by gravity. And acceleration due to gravity, we'll do this in meters per second, not feet. So it's negative 4.9, which is 1/2 the acceleration due to gravity, t squared. So it's gt squared. So this gives me the projectile shooting across. Now I have to have the projectile that's being dropped. Well, it's going to be 300 meters away, so I just place it, stick it out there at 300 meters. The nice thing about doing this parametrically is you get students thinking about the physical world and how they could model things like this with a calculator, and it's being pulled vertically by the same acceleration due to gravity. And once again, the students are going to have to deal with the window. So what makes sense for them? Well, if the projectile is at the 0 position horizontally, and the object that's being dropped is at 300 meters away, then I should have my x max be a little more than that. And a scale will just show me the tick marks. For the y min, I want the y min to show me the axis, so I'm going to have that go from -2 to 2. That should be plenty to show me that. And the scale can be 1 or 1/2 or something small like that. Now theta min and theta max, this is going to be how long does it take this projectile to move? Well, 6 units of time is pretty quick. It's actually going to be in the tenths, and we can let students figure that out on their own. And I'm going to make this go fairly slowly. So I'm going to have the point change set to 1,000th and execute that. Out of this, let's take a look at the drawing. And remember, what we're expecting to see is some projectile shooting out and an object coming down. And as the bullet moves down, we should see that these two intersect at the same, boom, there it goes. Now, a couple things I can do to change this. I can either slow down by changing in the window the point change here, or another thing I can do is I can change the initial velocity to be something a little slower. So if I chose that to be, say, 300, and this is a question we talk about with students, I want to make sure I can keep it on my screen. So let's see what happens. You can see it's slower. Boom. Now, it didn't get there because I didn't have enough time. So there's another thing for students to think about is, okay, so I didn't have enough time, I exit that, and I go ahead and change the window. So a couple things to change on the window would be the y min to maybe -10, and I've got to have enough time in t, and let's say that's going to be something like 2. And this will be the last, and we'll entertain any questions if you have any. And we'll go ahead and draw that. And boom. Once again, you can see that they do, in fact, intersect. So we've got a nice little physics model to show what we can do parametrically. So I've given you a lot to think about in terms of the power of parametrics and how they can be used a lot in mathematics, beginning even at the Algebra 1 level and having students understand that. I mean, I didn't study parametrics until I was in grad school many years ago, before the graphing calculators ever existed, and we did things parametrically in some calculus classes. So I'm going to wrap it up there. And Nathan, you let me know if we have any questions.
No questions.
For any of them.
No questions. Just a lot of food for thought.
Great. A lot of food for thought, exactly. So you want to final comments from you?
Yeah, sure. Thank you. Thank you, David. Just wanted to thank everybody for joining us this evening, and David for the presentation. And whoops, I lost my, there we go. That's what I was looking for. just wanted to make sure everyone was aware that if they'd like to learn any more about the calculator used this evening, you can sign up online at this address, go through a little course, and finishers are being given a calculator or the software, at least while supplies last. And I hope you enjoyed it. Thanks you very much, David.
You're welcome.